Hello guys, my name is Arun and welcome to my channel. This series is a series of tutorials on OpenMP implementation in Fortran. Now, in this tutorial, we'll be looking at an interesting concept which kind of really helpful in doing certain operations, okay, in parallel. And this concept today is called as sections class. Okay, now before I go about and explain that, let me just walk you guys through the program today. Okay, what I have here is I just have some five arrays A to E. Okay, each of them set by the dimensions m and n, whose values can be changed over here. Okay, and then I've set the values A to E over here. If you look at it, what I'm going to do I'm going to do four operations. One, with setting A, after setting A as some particular value, okay, I'm going to do some kind of a matrix operation. I'm going to do a matrix operation with B, meaning I'm using the value of A to do some matrix operation. I'm storing the value in B. Okay, now in this loop over here, what I'm doing is that I'm doing another matrix operation and storing the value in C. Here I'm doing another matrix operation and storing the value in D, and I'm doing another matrix operation over here and storing the value in E. Now you might ask me, hey, instead of doing all this, can't you just copy and paste these lines in the same loop so that you know you can do them better? Yes, you can do that. This is just for an example's sake. Okay, this is just for an example. Okay, I couldn't come up with at least I couldn't think of another example where how this will be useful, so this is just for the sake of example. Okay, what I've done is that if you look at it is that if you just run this program, let's say, it will run serially. Okay, so initially this operation will finish, and then this operation will be completed, and then this operation will be done, and then this operation will be done. But if you look at the variables, okay, in this loop, in this loop, and in this loop, and in this loop, the variable that you want to use is A, whereas variable B, C, D, and E, just get the value of A, modify them, and then store them. That's it. So meaning what can be done is that at the beginning of this program, from the somewhere after this line, okay, each of these loops can be separately done by individual processes. This loop does not need doesn't matter if you execute this part of the loop, this part of the code, even without having executed this part, it will work the same, because there's no dependence, because B need not be it doesn't matter whether you calculate B or not. C can be calculated independently. Similarly, that same argument holds good for D and holds good for E. So these are what I call as sections in a program. These sections are kind of independent in the program, okay, and they can add from a particular point. They can kind of behave independently. So it doesn't matter whether in which order you perform them, okay, which order you perform them. It doesn't matter. Okay, so if you give this to a serial, if you run this in a serial mode, all of them will be done one after the other. Each of these sections will be one after the other. So the logic logic that one can do over here when you're using parallel programming is this. What if we just divide this job? What if we just give each of these job to one processor or one thread? Now that being the case, if we do that, all of them will do the operation simultaneously and then finish simultaneously, right? So instead of having large number of time, it will make a big save it. It will cause good savings of time, right? So that's the logic over here. Okay, so that's the logic over here, and that's why we go with OpenMP sections. Okay, so how to do is as follows. Okay, now what I've done is that I just included the OpenMP parallel, because this will make sure that all the code that runs between this line till this line is done by all the threads. Now the thing is, now the parallel regime is started from here till over here. This highlighted region is the parallel regime, so all the 4 threads will be active here. And what I've done here is that I've included a new class, a new option or a command called as sections. Now what this sections does is that it tells the compiler that, hey, tells the executable that, hey, see, I've started an a parallel block. When you come across sections, careful, I'm dividing the job. Just to keep note that I'm dividing the entire job set of instructions into small divisions, and each division has to be done by one thread, and that's what our sections does. Okay, now once you start an OpenMP section, okay, the entire code between OpenMP section from the start and the end, okay, has to be segmented, has to be divided so into individual chunks. Okay, once you divide that, okay, you just have to assign each part of the code to one section. So this part of the code is one section, okay, defined by the keyword OpenMP section. Okay, now what I've done here is as follows, like the iterating variable j and I, okay, j and I, and the thread number is common for all the sections over here. Okay, so I'm going to run this in parallel mode. So what happens is that because of race conditions, I and j value will be modified by each thread. So, and even the thread number will be modified by each thread. So what I'm doing is that I'm just making the iterating variable I and j and the thread number, okay, to be private, so that if once this is done, each thread will have its own copy of I and j, so they will not go and interfere with other threads I and j and thread number value. So you're avoiding the race condition, and I don't have to put b, c, d and e in race as private, because as per this code, b will be accessed by only one thread, c will be accessed by only one thread. So, similarly the same applies for d and e, so they don't have so it's not a problem. And besides, a was shared, a is not getting manipulated, the value of a is being used, that's all. So a is shared, so you don't have to mention that, so it's not a problem. Okay, so the race condition comes in I, j and thread number, which is avoided using the private class over here. Okay, now once that is done, okay, we define the section and the section of the code. I just say that thread number equals OpenMP get num thread. With this command we get the thread, and I print like when you run in parallel, it prints like section 1. This is matrix squaring, given by the nickname mat_sq, whatever it is. This is just for our view convenience. I said mat_sq is started by thread number, so comma thread num, so that we'll know that which thread is performing this section. Okay, and it will do this job, and once this job is done, this print statement will pop up and say that, okay, this job is finished by this thread. Okay, this will give us an idea, okay, which thread is doing which job at any instant. Okay, next what we can do is that once this is one section, to indicate that we are going to write another section, we don't need an OMP end section. What we need is that we just have to write this line again, OMP section. Now what this does is that it inherently terminates this to be blocks this region to be one section. So you don't need an OMP end section here. So it's understood. Okay, so this part becomes another section. Okay, till this line, because from here you have another OMP section. So from this line to this line, it's one section. So here I'm doing the same, getting the thread number. I'm printing that section 2 is being done by this thread, and then I'm doing some thread operations. Okay, I'm doing some operations. Okay, you don't worry about it. Just an example. So it's not a big deal. You can do anything you want over here. And then similarly, I'm doing the same thing for other next section, and then I'm doing the same similar thing for another section, and each time I'm having a different operation under the loop. Okay, and now what I've done is that I've created my 4 sections, and then I have to tell the compiler that my sections are over. So I do that by telling OMP end sections. Now with this command, all the sections are over. Okay, and now I have to close this parallel block. So to do that, I say OMP end parallel, and thereby the parallel block is over. The parallel block is over. So what happens is that what will happen is that when the threads when the process execution comes to this point, the threads will become active, okay, and each of them will start will be ready to do all the job from here to here. Will be ready to do each of the job all from here to here. Once they come across sections, they'll understand, okay, I'm dividing the job into 4 parts, so each of them go and do one part, one section, and then they terminate. Once all of them finish, they'll just wait over here, and then the threads will join out, and then only one thread does the remaining operations and so on. So this is essentially what we did in the last time. Okay, so let's run this. So what I'm going to do is that let's run this in the parallel mode to see what's happening. Sorry, the serial mode to run what's happening. The thing is, I have included this flag called as MC model equals large in both the compilation and during the execution. The reason is because there is some kind of a memory issue which is popping up in my laptop. When I compute this, I'll just let you guys know. I'll show you guys what's happening in a minute. Anyway, for now, let's run this in serially. Okay, this is so I'm going to compile the code and then compile the program and then collect the object variable and produce an executable sections.exe. Okay, and so let me clear this up. Okay, and let me keep the task monitor nearby so that you guys can have a look at what's happening. Now bash that as such. Okay, and it's taking some time. If you look at it, the RAM just shooted up. The overall program from the beginning till the end took about maybe, let's see if my guess is right, about 4 seconds or something. Whereas this part from the part of the code from this line called CPU_time till this part took about 1.448 seconds. This is in serial mode. Now let's do this in parallel mode. Now to do this in parallel mode, it's simple. Just like in my previous programs, you do that and then run this. Okay, we are getting we are able to get a speed up. We are able to get a speed up of close to 3, and the time taken was 0.522 seconds. If you clearly notice this, the time taken has reduced substantially, but not too much, but slightly. Okay, so if I were to run this again, you can run this again if you want. It will take about another 0.58 seconds to do the stuff. Okay, now here's the thing. So that's about with the sections. Okay, now let me tell you guys what's happened, what I mean by this extra flag over here, MC model equals large. So what happens is that if I were to compile this serially, let's say, if I were to compile this serially without the OpenMP flag and without this MC model large flag, what happens is that if you run this, now it's working fine. Hold on. Okay, I forgot to save this. Okay. What happens is that it throws up an error stating, the compilation, if you look at this line, the compilation was successful, but when you try to execute it, it shows an error like sections.f95, which is our program. There's a problem in the function main. Relocation truncated to fit r_x86_64 something and against bss. We get these 2 errors, and it says that there's an exit status, so it's the linking was a problem. The object files were ready, but the object file was used to convert into an executable. It was not possible, so it threw an error, and what happened is that you don't have an executable ready. Okay, so when I tried to look at it, I just copied this line, relocation truncated to fit this something this is. Okay, I tried to look at it, and I looked at the first question, not this question, this was related to Intel. Since I'm using Fortran, I clicked this link, and it took me to this stackoverflow.com link, wherein some other person had a Fortran 90 code in which he wrote something, and he got a similar error like what we had. He says that he says that, you see, relocation truncated to fit against symbol, something like that, and he got the same error. When I looked at it, this one was different. This answer was not helpful. I don't know. I didn't understand what this answer meant, but anyway, this answer was really helpful. This person says is that when you're allocating memory and stuff, and when you're allocating static memory or something like that, and what happens is that sometimes the static allocated memory can have some limitations. Okay, by default, when you compile a program, let's say, and do some operations with that, what happens is that the static memory allocation will be memory allocation will be limited. Okay, and when you compile them and link them, there might be some linking issues. So what you have to do is that one workaround is that when you compile the code, you just put MC model equals large, or MC model equals medium. You have to put this flag, and if you want to know how exactly this works, you just click this link, and I went to this link which goes to over here, and there's a big explanation as to what this means and everything. Okay, they just go into the memory model and stuff, memory model and stuff, and they go about with it. I guess, for our program it's not necessary, but for those of you guys who are really interested, who want to know what exactly is happening, you can just have a look at it. For this program, it's not necessary, but just a heads up in case you guys run into a problem like this. Okay, this problem comes when your memory is too large. For instance, if you look at this problem over here, I have m equals 10,000 and n equals 10,000, so you have like 10 power 8 elements. Each of them has like 8 bytes of memory, so it's quite a large memory size for each variable. So what I've done, what I'm doing is that instead I'll just reduce this to 1000 by 1000, thereby reducing the memory by 100-fold. Now if I run the same shell file which I used before and run the same, it compiles properly. It compiles, links properly, and does everything properly because the memories are within limits. The moment I increase the memory by a certain value, it gives me this link. It gives me this linking error. So this is just a heads up. So in case if you guys find some memory issue or something like that, okay, the saying that relocation truncated to fit something like this, just put MC for at least as a short workaround, just put MC models equals large or medium, depending on what program you use. Okay, now with this being said, now let's concentrate on the how do I say, OpenMP part of it. OpenMP part of it. Okay, now let's do this. Now if I were to run this, okay, now let's look at the results. First of all, what happened is that it says section 1 mat_sq started by thread number 0. So since we put 4 threads over here, okay, it clearly section 1 is this section has got to be executed first, and that execution was done by thread number 0. Okay, thread number 0. So thread number 0 started this execution, okay, and it started working on it. And as and when it started working and section 3, okay, which is namely this section over here, okay, this section 3, which is matrix, which is given a nickname mat_square, okay, this section was started by thread number 3, okay, and after this section 4, which is this section over here, it got which is given by a nickname mat_cof. This is started by thread number 2, okay, and after that section 2 started in the last. Okay, section 2 started in the last, and section 2, which is this one, this is started by thread number 1. So if you look at it, all these 4 sections, okay, are individually done by individual threads. Okay, and what happens is that section 4 which got started third finished first. Okay, and it's, if you look at it, the same thread which started and ended the thread, sorry, it started and ended the process, finished the work. Okay, so that's a one-to-one correspondence. Next after that, section 3 which started executing second, okay, finished second. Okay, and then section 2 which got finished started last, finished one before, and section 1 which started in the first, ends last. So clearly, if you look at it, you know, this distribution of which section is done by which thread is random. So if I were to run this again, if you look at it, you know, it will be quite random. For instance, section 4 is started by 2 over here, and here section 4 is started by thread number 3 over here. Okay, so there might be similarities, but in general there will be a lot of differences. Okay, the pattern will change, and pattern will change and everything. Okay, now let's do something. Now we have 4 sections and we have 4 threads, right? Now let's see what happens if the number of threads are less than the number of sections. Okay, for instance, here I just put the number of threads to be 2. Okay, now let's compile, build and execute this code. Okay, now let's see what's happening. Now it says here that matrix square section 1 is started by okay, started by thread 0. Okay, the section is started by thread 0. Now section 2 is gets started by thread 1, which is okay. Okay, now even before some other job can be finished, section 2 finishes section 1. So section 2 got finished by thread 1, and then thread 1 takes section 3, starts section 3. Okay, and then before section 3 can be finished by section 1, thread 1, section 1 is completed, which started over here. It gets completed by thread 0. Okay, and now section 1 is still running, so thread 1 is still running, so thread 2 go and start section 4, and then it starts working, and in the meanwhile section 3 which was started by thread 1 completes it, and then section 4 which was initially started by thread 0 completes the job at the end of the day. Okay, so if you look at it, let's say we have more sections than the number of threads. The threads will do more number of jobs at a time. So what happens is that they might do 2 sections or 3 sections, but all those sections will be done serially. Okay, the job will be split among the threads, but still they'll be done serially. So let's look at a case wherein we have an uneven distribution. For instance, when we put thread to be number of threads to be equal to 3, 2, what happens, and we have 4 sections, so it's logical that the 2 sections will be done by one thread, 2 sections will be done by the other thread, something like that. Now let's see how this dynamics go by for 3 threads. Okay, now watch. Now what happens is that 3 threads are active at any instant. Okay, any thread which completes one of its job takes the other job and does it. So what can happen is that if you have 3 threads and 4 okay, now let me write this in the journal so that you guys can have a understanding about it. So threads equals 4, sections equals 4. So section per thread will be 1. That's quite obvious. Now if your threads equals 3, let's say, and sections equals 4, sections per thread this can be 2 comma 1. Okay, in some worst case, this is 2 comma 1, and that's how it will be. Okay, so in cases like threads equals 2 and sections equals 4, what can happen is that sections per thread, okay, it's usually 2. Okay, sometimes it can be 3 comma 1. What I mean by this is that, okay, sometimes thread 1 can take two jobs and thread 2 can take 2 jobs and finishes it. Sometimes what happens is that thread 1 can take 3 jobs and thread 1 can take just 1 job and finishes it in the process. Reason is because the jobs might be overwhelming. For instance, what I'm going to do here is that I'm going to reduce the matrix number, so that the size of the matrix, so that it's plausible. The calculations are possible. Now what I'm going to do is that I'm going to do some matrix multiplication kind of a thing. Okay, now what will happen is that, now let me run this with 4 threads. Okay, this part will, because of this additional loop over here, this will take more time. Okay, now let me go to the terminal and let me run this in OpenMP. If you look at it, section 1, which was started with thread 0, started first but ended quickly, and ended at the last. So if you run this again, if you look at it, section 1 takes the largest time. Okay, it takes the largest time to complete. So clearly, when compared to these sections like section 2, section 3 and section 4, the amount of work on section 1 is heavy, is much larger. So obviously in this case, when you have 4 threads, each of them will complete one after the other, but the entire program will be over when all the threads are completed the jobs. So what happens is the 3 threads in this condition, 3 threads would have finished the job and would be waiting for the 4th thread to finish, and only when the 4th thread finishes, all the threads will join together and then continue with the serial part of the code. Okay, now what I'm going to do is that, let me set this to thread 3, number of threads to 3. Okay, now I run this code, check what happens. So as per our logic, what we saw is that thread 0, which took section 1, okay, completes last. Fairly obvious because this loop is more computational intensive and there are a lot more iterations to be done. Thread 2 does thread 2 does section 2, and thread 1 does section 3 and then section 4, one after the other. It finishes section 3 and then it starts section 4. Okay, and so forth. Now let's put this number of threads to be 2. Okay, now watch. Because section 1 has extensive amount of load, what could happen is as follows. There are 3 possibilities. There are 2 possibilities if I'm right. One is that each thread will do 2 jobs at a time, two jobs one after the other, 2 sections, or else one thread will do 3, other thread will do just 1. Okay, watch. You see this? Thread 0 started section 1. Okay, section 1, thread 1 started section 2, and as and when section 2 is finished, okay, thread 1 looked at the problem. Thread 0 is still finished working on section 1. So section 1 took thread 1 took the section 3 and does the job. Okay, and after that it looked at whether thread 0 finished. It didn't, so it took another job, section 4, and then and then it starts finishing it. Even after that, section 1 isn't finished by thread 0, so it just waited, and then section 1, after section 1 is finished, both of them join together, and then the program terminates. So clearly what happens is that when you have an uneven load sharing between sections, okay, threads tend to take some threads tend to do more sections than what would be necessary. Okay, and in the case wherein if you give like more number of threads than what the number of sections required, what happens is that one of the thread will not be called upon. So here, if you clearly look at it, thread 0, 1, 3 and 4 work, but section 2, thread 2 was not at all called. So if I do this again, by a remarkable coincidence, thread 2 was not called again. So if I run this again, here thread 3 is not being called, whereas thread 0, 1, 2 and 4 are called. So what happens is that since there are only 4 sections, you just need only 4 threads, so one thread is idle. So that's one of the thing. The thing you have to keep in mind is that when you go with sections, make sure that you keep the number of threads in consideration, so that the load is evenly shared between them, so that even if one thread finishes, other threads will be active. Other threads will be active. Okay, that's all I have for you guys in this tutorial. Thank you guys for watching, and hopefully you guys got a lot of got a better idea and intuition about how to use sections in OpenMP, sections operations in OpenMP. Okay, next tutorial I'll come up with something similar or interesting to look at. Okay, till then, thank you guys for watching, and I'll see you guys next time.